Hello everyone, this is Mike Dowding with the SD Mines Physics Department, and we're going to finish off Chapter 7 with this video today. And our topic is work done by springs. And what we'll do is go ahead and review over a couple of things concerning work and springs separately, and then we'll combine the two. So going back to the beginnings of this chapter, our definition of work is a change in energy, and that change can be accomplished by applying a force over a certain displacement. And just as a reminder, that cosine theta term is a means of comparing the angle relationship between the two vectors, force and displacement. And so the more force that we have in the direction of the displacement, the more work that we will accomplish. And it is possible to have negative work. That can be done if the angle theta exceeds 90 degrees, because anytime we evaluate cosine at an angle greater than 90, the result is a negative. Another way that we can evaluate the work done by a force is if we are given the component values of each of those vectors. And this was explained in a previous video, but we can take the product of the like terms and then add up those products, and we will get the same result as what we get from the magnitude and angle version. And then we have the spring force, which we found out has a value based on little k, which is the spring constant, and little k measures the stiffness of the spring. So the larger the spring constant, the more force that the spring can produce. But our spring force is variable. It depends on how far from the equilibrium position our spring is displaced. And so this was also discussed in a previous video, but we're going to go ahead and label the equilibrium position as 0, and then if we measure in either direction, positive or negative, we will see an increase in the magnitude of the spring force. And that spring force will always point towards the equilibrium position. The spring always wants to return to equilibrium. So now we want to take this information and combine it so that we can find out how much work is done by a spring. For this, I am going to consider a mass of m, which has been attached to our spring. That spring is currently at its equilibrium position. And then we will displace the spring a certain displacement d. And in doing so, when we displace the spring, that requires us to apply some kind of force to remove the spring from equilibrium. But as that is happening, the spring will apply a counter force in an attempt to return to equilibrium. And if we try to apply this to our dot product method of evaluating work, the first thing that we should notice is that there is an angle relationship of 180 degrees. So right away, we should realize that there is negative work being done by the spring because of that cosine relationship. So work is going to be negative. But the problem that we're going to run into is this current method of evaluating work assumes that we know what the magnitude of the force is. And that's the big problem, because as we continuously remove our spring from the equilibrium position, every little displacement is going to cause a change in the magnitude of our spring force. And that's the result of the equation that we have for the spring force, because it is dependent on position. Work is a scalar, and work is the measure of how energy is changing. So is there some way that we can figure out the individual infinitesimal amounts of work that are being done, and then just add all of those up after we're done with the total displacement? And that right there is the foundation of the integration process. We want to take all of those individual infinitesimal little amounts of work and we want to add them up. So we're going to modify the equation that we have right here to take into account how our force is changing with respect to the changing displacement. And we will need some limits so that we don't end up with an indefinite integral. But for right now, we can just put in initial and final position. From there, we will insert the function for our spring force, and that's our function right there, negative kx. We are evaluating with respect to x, and so the result is negative k x squared over 2 evaluated at the limits. So there's the work done by spring. And I'm actually going to leave this in this form. I'm not actually going to evaluate it at the limits just yet, because when it comes to the displacement of the spring, this spring, if we were to stretch it out and then release it, well, the spring would pull itself back to equilibrium, but in doing so, it would pick up a little bit of speed, which would bring it past the equilibrium position to some final compression point, and then the spring force would push it back towards equilibrium again, and so we would just see the spring oscillating back and forth forever, unless there was some kind of a dampening force like friction, which in the real world there is. Air resistance could also be considered, but for right now, we'll consider a frictionless system, no air resistance, and that means that our spring is just going to keep bouncing back and forth between two extreme values. We don't know what those are just yet, but let's go back to the original idea behind this discussion, which was that we were going to take our spring from the equilibrium position and we'll go out to that distance of d. So how much work will the spring do in taking us from 0 to D. Well, now we can plug in the values of our initial and final position, and in doing so, our expression evaluates to, and I'm gonna factor out the k and the 2, and that will leave me with x squared evaluated at the limits. So x squared evaluated at d minus x squared evaluated at 0 gives us negative k over 2d squared. And at this point, all I really need is a k value that tells me how stiff the spring is. So maybe we do 20 newtons per meter for the k value, and then we can let d equal 10 centimeters for 0.1 meters. And it's probably worth mentioning right now, it's far more common to see the spring constant actually given in newtons per centimeter, because a lot of the springs that we work with are probably not going to be operating over meters of displacement unless you have a really, really big spring. So it is probably more commonplace that you would see this spring constant given in newtons per centimeter. So let's see, in that case, we would need to change, and that would give us 0.02 newtons per centimeter. So this would be the more common way of seeing the spring force expressed. However, for our purposes, we need the standard units of newtons, meters, kilograms, seconds. So I'm going to go ahead and plug in the 20 that we had over here. So we have negative k over 2. Our displacement was 0.1 squared. We'll go ahead and plug all that into our calculator. Oops. And I am getting negative 0.1 units. Well, we just figured out how much work was being done by this spring, and so work is a change in energy, which means we have done negative 0.1 joules worth of work, moving the spring from the equilibrium position out to that 10 centimeter mark. Well, we said the spring would eventually bounce back, so let's see what happens if we stretch the spring out to that 10 centimeter mark and then let go. So we're going to remove our applied force, and in doing so, the spring is still going to want to return to equilibrium, but now the spring is going to travel in the opposite direction. When that happens, now our spring force and our displacement are pointing in the same direction. And that means that our angle relationship is no longer 180, but rather 0. And so we should expect to have positive work done. Well, what does that mean for the expression that we went through? Do we have to redo the integration? No. This was why I wanted to keep the equation in its general form, because really all I need to know for for the work done by a spring is where are we starting and where are we ending. In this case, we're starting our displacement out at the 10 centimeter mark, and we're going to end up back at the equilibrium position. And so when I evaluate everything in terms of the limits, all that happens is that those values get transposed. I now have 0 squared minus d squared, which I've got a negative out front on the k. I have a negative attached to the d squared, so now there's a positive kd squared over 2. And we've already evaluated that. And so there is a positive amount of work done in returning the spring to equilibrium. So what is the net work done in getting the spring from the equilibrium position out to the 10 centimeter mark and back? Well, we already saw that in stretching the spring out, there was negative 0.1 joules of work. In letting the spring return to equilibrium, there was positive, and so the net work done by the spring returning to equilibrium is 0. Well, what about a compression? In this case, we saw the spring get stretched out. So what if we were to compress the spring instead? And this will go a bit quicker, because if we compress the spring, we're removing the spring from equilibrium. The spring is going to fight us. This time we'll let the spring go back to a displacement of negative d. We're expecting to get negative work out of this because our two vectors are in opposite directions. But we've already done all of the math required to evaluate work done by a force. All we have to do is plug in the appropriate limits. So where are we starting? Well, we're going to start at the equilibrium position again. Oops, sorry, I didn't mean to erase all that. We're starting at the equilibrium position again and going out to a final value of negative d. So we're going from 0 to negative d. Now do be careful with your algebra. We're going to evaluate all of this stuff. We'll take the negative k over 2 out front again. And then we have to evaluate x squared at the two limits. X squared evaluated at negative d means that we have negative d squared. And then we have to subtract 0, so 0 squared. But negative d squared produces a positive d. There's this other negative waiting out front, and so we're once again getting negative k over 2d squared. And if negative d just went back negative 10 centimeters, well, we're going back to negative 0.1. How does that evaluate? So our k value was 20, we have our 2, we have our negative 0.1 squared. Well, all of that is still going to evaluate back to negative 0.1 joules. So as it turns out, it doesn't matter which way we are displacing from the equilibrium position. Anytime we move away from the equilibrium position, we're going to do negative work. And as it turns out, we do the same amount of work for the same amount of displacement. So this is worth mentioning over here. Let me start over here. We'll say a spring will do negative work when displaced from the equilibrium position. But then we also know that if we allow the spring to return to equilibrium, then the spring will do positive work. When it is returned to the equilibrium position. And we can confirm that with this compression example. If we allow the spring to start at negative D and return to the equilibrium position, remember our spring force always points towards the equilibrium position. So now our vectors are running parallel. We expect a positive amount of work to be done. We are starting our displacement at negative D. We are ending at 0. So we come over here and adjust the limits on our integral. Starting at negative D, ending at 0. All that does is transposes the limits. So we're now ending at 0. And we have to subtract the evaluation at the initial. So let's count how many negative signs we have here. There's the 1 on the K, 2, and then 3, 4, because everything has been squared here. So 4 negatives. That's going to result in a positive outcome for the work. But we're using the same numbers. So let's see here. That one turns positive. This one can stay negative because we're squaring things. And so we get positive 0.1 joules. So we can also say that the net work done by compressing the spring and allowing it to return to equilibrium is also 0. So there's work done by a spring. And at this point, what I'd like to do is just take a little bit of a break from the math and the terminology of the spring there and consider what does it mean for a force to do negative work over a closed path, because that's exactly what we saw the spring do when we stretched it out and allowed it to return to equilibrium. We also saw that happen when we compressed it and allowed it to return to equilibrium. So a force that does net work equal to 0 over a closed path is called a conservative force. Because what we are doing when we move from one location to another and back again. If we are doing equal and opposite amounts of work during that closed path, it means that we are conserving the energy of the object. We have effectively added the same amount of energy that we have taken away, and vice versa. And so by conserving the amount of work that's done, we call this a conservative force. So obviously a spring force falls under that definition. So a spring force is going to be conservative. What other forces are there that could be conservative? I'm just going to do one more example here. We'll go with gravity. So if I take a ball and I drop it a certain displacement, the amount of work done by gravity would be our gravity force dotted with our displacement, and we can go ahead and sort of skip to the end here. We know that the angle relationship between these two vectors is 0. They're both pointing down in the same direction. Cosine of 0 is 1, and so the work done by gravity getting the ball to the ground is mgd. Now that's a general solution. We can always come back and plug in a mass and a displacement value, but that's the work done by gravity as the ball falls to the ground. But I want to see if gravity is a conservative force. So is gravity a conservative force? To answer that, we need a closed path. And the definition of a closed path is that you end up back where you started. Well, so far, I've gone from here to the ground. If I expect to get back where I started, then I need to move the ball back up. So I would physically have to pick up this ball and return it back to its original height. But as I do that, how much work is gravity going to do as I bring that ball back up? Up here, this was the amount of work done by gravity as the ball was falling down. So now I need to figure out how much work is gravity going to do when we pick the ball back up. And most people look at this expression and they're like, well, it's exactly the same thing, except there's one very critical change, and that is that when we pick the ball up, we are displacing the ball up, but gravity is still pointing down. So we actually have a cosine relationship of 180, and cosine 180 is equal to -1, so we actually have a negative mgd for work done by gravity as we pick it back up. So now we have accomplished our closed path. We allowed the ball to fall down, we brought it back up, so our total displacement is 0. That is the definition of closed path. But then when we go to add up the work done, we have a positive mgd and a negative mgd. We add that up and we get a net work of 0. So it looks like gravity is also a conservative force. If there are conservative forces, does that mean that there are non-conservative forces? And the answer is yes. There wouldn't really be a point in defining conservative forces if there weren't other types of forces out there. Well, conservative force is a force that conserves the work done. In other words, it conserves the energy for the object. So now we need to consider, are there forces out there that don't conserve work done? We have a number of options that are out there. Obviously, we've already seen gravity, but what about a normal force, or a tension force, or friction? All of these are forces that we would have to consider. We could consider centripetal force, but really centripetal force is just one of the forces mentioned above. So we really probably don't have to consider that. We've already confirmed gravity. We've already confirmed the spring force. So we've confirmed the spring force, we've confirmed gravity. I'm going to go ahead and let you confirm the normal force and the tension force, but I will tell you now that they can be conservative. The real question is, what about friction? Is friction a conservative force? And if you remember our discussions in the previous chapter, if I apply a force to a mass and I start dragging it over a rough surface such that there is friction in the system, well, friction wants to oppose motion. And the only way that I can answer the question of whether a friction force is conservative or not is I have to allow this block to move back and forth. And whenever we're moving, we have to work with kinetic friction. So let's move this block to the right. If we do that, our friction force opposes the direction of motion. So we'll plug all of this into our dot product for evaluating work. Now for a friction force, kinetic friction specifically, the equation is mu kn, and we could do some extra work in this problem to figure out what the normal force is, but for right now, we're good in knowing that we can find that friction force. So I have a value that I can plug in here. I can define some value for the displacement, but then we have an angle of 180 between our friction force and our displacement. So long story short, we're getting work that is negative. Our friction force is working against us. Okay, so that's moving to the right. What's going to happen if I start moving the block to the left? So now let's assume that the block is over on the far right side somewhere. So we've displaced a distance of d, but now we need to take the block back. Well, to do that, I'll apply my applied force, and we'll move the block to the left, but friction always opposes the direction of motion. And so we once again end up with work that is negative. Everything that we see here is going to be exactly the same as what we had moving this block to the right. Friction does negative work moving to the right. It does negative work moving to the left. So what's the net work? It's not zero, because we have two negative quantities, and when we add them together, I get something more negative. Friction is not a conservative force because we did not get a net work of zero. We got a net work that was obviously very negative. And friction will never do positive work. If you remember in some of our past discussions, we said that it was possible to have positive or negative work done in a system. When you get positive work, what you're doing is you're putting energy into the object. So if you have a mass and you're doing positive work on that mass, you're putting more energy into that object. If you have negative work that's being done, then you're taking away energy from that object. And this is why anytime you have something that's sliding across the surface with friction, eventually that object comes to a stop, because the friction takes away all of the kinetic energy of that object, and it's going to convert that energy into heat. But that's going to be a discussion for the Chapter 8 material. So what we're going to do to finish off the discussion for today, even though we've gone over the math behind how much work is done by a spring force, what we need to do now is consider the math behind any variable force in general. A spring is a variable force, but we could have other variable forces out there. And the way we're going to do this, the way we'll start our discussion, is let's consider just a constant force. Let's take a constant force of 20 newtons, and we'll allow it to work over a displacement of 5 meters. So how much work is done by this constant force? And that's pretty straightforward at this point. We know what the magnitudes and angle relationship are for this system. We have a force of 20 newtons, we have a displacement of 5, we have an angle of 0 because our vectors are parallel to one another. So we're getting 100 joules of work. No problem. Let's take that same set of numbers and let's graph it. Let's graph the displacement versus the force. And this probably isn't going to look all that glamorous, but we're going to displace over 5 meters. And our force, well, our force is constant. It's 20 newtons. If I graph this, I'm just going to get a straight line. And that line, I drew it a little too far because we're only going out to 5 meters. That's just a straight line. And you're probably thinking, well, how does that help us? Well, consider what's underneath the line. And consider what we did with the spring force. We integrated the function of the spring force to tell us how much work was being done. But another Another reason to use the integration process is to find the area underneath a function. And for us, the area underneath this force function is just the length times the height, which is 20 times 5, which is 100. So the area underneath that force function, even though it's just a line, it's still a function, is 100. And, well, that's exactly the work that was done. And that's what the integration does. The integration is just the calculus way of adding up all of the area that's underneath that curve. So what did we do for the spring force? Well, our spring force, if we go with the magnitude of the spring force, because the spring force is actually a negative, but if we go with the magnitude, and we were to measure that, well, the ratio of the spring force to the displacement, that was K. And that was the slope of the line here. And so if I start from 0 and I go out to some final position, we'll call it D, with our spring force, what is the area underneath that function? Well, that's a triangle. And back in geometry, we learned that the area of a triangle is 1/2 the base times the height. So what's the base? Well, the base is the displacement. The height is the magnitude of the final force value evaluated at D, which is kx, except x is equal to D at the final value. And so all of this ends up being 1/2 D times kd, or half kd squared. And then if we bring back in the fact that the spring force is actually negative, then the work is the area under the curve, which is negative. We just have to remember that we are evaluating from initial to final values. So we're getting exactly the same outcome that we got from the integral process, but in a graphic representation. So now, for a true variable force, what if you had a force that looked something like this as it displaced? So we want to figure out how much work is being done. Just a minute. Well, that's not going to be the easiest thing for us to figure out in the graphic sense. So that's why we're going to let the calculus do the work for us. The only thing that we would need is some kind of function relationship that actually tells us how the force is changing with respect to position. Otherwise, we're probably not going to have any hope of figuring out just how much area is underneath this graph. But that means that we should be able to take any force expression. Well, maybe we've got this polynomial expression here, which is describing a changing force with respect to position. And I'd like to know, sorry, it's not a spring force. I'd like to know how much work this force does if we go from -2 to +5. So to do that, we will plug our force expression into an integral and evaluate it at the limits, which have been provided to us. So we need to integrate this function from -2 to +5. And when we do that, we get a 3x cubed over 3 plus 2x squared over 2 minus 7x. The 3's and the 2's are going to cancel out, so we'll clean that up. This is what we're getting when we evaluate, or excuse me, we haven't evaluated yet, but this is what we get after we integrate. And now we're going to evaluate. So we need everything evaluated at 5, which will be 5 cubed plus 5 squared minus 7 times 5. And then that has to be subtracted, or we will subtract everything evaluated at -2. Calculator time. Oops, I forgot to plug a 5 in there, so we'll do that right now. So my calculator says that 5 to the 3rd power plus 5 squared minus 7 times 5 is 35 is 115. And then we'll subtract what's in the second parenthesis set. -2 cubed is -8. And then 2 squared is 4, so we're adding 4. And then we have a -7 times a -2, which is a +14. And that's giving me 10. 115 minus 10 is 105. So that is how much work this force function does in moving us from -2 to +5. And all I can assume at this point is that we had meters for those position values. But that shows us how we're going to deal with really any kind of variable force with respect to position. And that brings us to the end of the video, and as such brings us to the end of Chapter 7. So the next video we will be starting Chapter 8 material. However, we're still going to refer back to quite a bit of the Chapter 7 material as we transition into Chapter 8. So until then,